So now if we plot two values against each other for all measurements that we have, so x is on one axis and the y is on the other axis, and each of these dots here represents a data point. This is called a scatter plot. And for scatter plots, you can construct a regression line. Okay? And in Excel, you just right-click on the data cloud, on all these data, and you choose Add the regression. Okay? And you can choose a linear regression, and there's a little bit of details here. But anyway, you can also display the equation, and you can display the R-square value. And this is shown here in this graph here. Okay? You can see here's all my data. Good. And you have the regression line. It's this red dotted curve, and this is the equation of this line. Okay, and linear equations, they have two parameters. The first one is the slope of your line, and the other one is the intercept with the y-axis. This is what you get if you set x to 0. Okay, this is what we call a linear equation. Okay. And this regression line is actually calculated such that the average distance between the data points and the line is minimized. So this is how Excel or other software suites calculate the regression line. But there's also something else. There's the R-square value. You can also choose to display the R-square value. In this example, it's 0.88. Okay, and this one is like this decimal fraction, but it's similar to percentage. Yeah, 88%, 88.6%. Okay, so that's ranges between 0 and 1. Okay. So the R2 square value, called the regression coefficient, indicates how well the data are described by a linear relationship. If you have a value of 1, 100%, you get a perfect correspondence. If it's 0.75, there's a good correspondence. And if it's less than 0.5, there are issues. I want to give you some examples, and it's very, very important. Some very, very important details. So first of all, okay, if you compare an observed value with a theoretical value, you actually expect a one-to-one correspondence. Yeah, so this is in your practical, you observe, you expect that the speed that you derive, you expect it to be the same as the theoretical speed. And if you plot now the data in a scatter plot, what you expect is that your data are along a line, the diagonal. Okay? So if you get a 4 on the x-axis, you get a 4 on the y-axis. This is what you expect. Okay, and then if you get a high correspondence, then the data should sit on that line. So that's one thing. Now the second point, and this is a really important point. What happens if you have an error, one measurement which is totally wrong? Okay? We call them data outliers. That's a small number of unusual values that have no obvious relationship to the other. Often these are errors. Again, I'll show you one example. So just look about here on the left-hand side, you have observations, okay, and you have an independent variable and the dependent variable, and you plot them in a scatter plot. You have a data, and you put a regression line through. And this example, very low R-square value, 0.02. Okay, there's no real relationship. This is sort of between these two variables. Although you can put a line through there, there is no linear relation. However, let's see what happens if you have one wrong measurement. This is on the right hand side. Look here on the right hand side, you have one freak measurement. You put through the regression line. Look, all points are relatively close to this line. You get a high R-square value of more than 82%. Can you believe it? Okay. And you think, yay, it all makes sense. It is a super result. No, it's not. It's all because there's one error in it. This is the problem. So you really have to be take care of outliers. You have to remove errors in your statistical analysis. Right? That's very, very important.